Somewhere in the deep universe, a single object shines with a power so extreme that it outshines entire galaxies. Its light has travelled for billions of years to reach us, carrying the story of one of the most violent engines nature has ever made. Tonight, this journey moves from the edge of the cosmos to the darkest boundary in existence. If this kind of space documentary is the reason they come here, they can like the video, subscribe, and continue deeper into the universe. The light from the record quasar begins its journey when the universe is still young by present standards. More than 12 billion years still lie between that distant moment and the Earth that later receives the signal. The object already exists as an active galactic nucleus, a galaxy core made intensely bright by matter falling toward a supermassive black hole. Yet in this first region, the main subject is not the core itself, but the age around it. The universe at that time is not a finished structure spread into calm maturity. It is a denser, busier, more crowded cosmos, with galaxies closer together on average than they are today, with gas moving through a younger pattern of assembly, and with much of cosmic history still ahead. The expansion of space has already been underway for a long time, but the universe is only a small fraction of its current age, and the light that leaves this source enters a cosmos that is physically smaller than the one in which it is later observed. In that early age, darkness does not mean emptiness. Space already contains vast numbers of galaxies, stars, and clouds of gas, but their balance is different from the balance seen in the nearby universe. The average galaxy has had less time to settle. Many systems are still building themselves rapidly. Gas remains more abundant in many galactic environments, and because gas is the raw material for star formation and black hole feeding, the young universe tends to be more active. Astronomers often describe this broad era as one in which growth is common. Galaxies gain mass, stars form at higher rates, and some central black holes shine with unusual strength. The quasar belongs to this general age of vigorous change. It is not bright in isolation from cosmic history. Its brightness makes sense only because it appears during a period when the universe still contains large supplies of gas, and when structures are still gathering mass with great efficiency. Seen on the larger scale, the universe at that time already obeys the same basic rules that govern it now. Gravity gathers matter, light crosses expanding space, atoms absorb and emit radiation in precise ways. Yet the proportions are different enough that the era has its own character. The microwave background left from the hot early universe still fills all of space, as it does now, but it is warmer then than it is in the present age because the whole universe is more compressed. Chemical enrichment, the gradual build-up of elements heavier than hydrogen and helium inside stars, has advanced far beyond the first generations of cosmic history. But it has not yet reached the degree seen in many mature galaxies nearby. There has already been enough time for stars to live and die, for galaxies to brighten, and for black holes to gain enormous mass. Yet there has not been enough time for the cosmos to thin and age into its later, quieter state. The light of the quasar therefore carries a double meaning. It comes from one object, but it also serves as a report from an era. This era matters because distance in astronomy also means time. When observers measure a great redshift, they are not simply measuring remoteness. They are measuring how far back along the history of the expanding universe the light begins. The stretching of the light by cosmic expansion shifts the signal toward longer wavelengths and records the scale of the universe at the moment of emission. For this quasar, the redshift shows that the source belongs to a very early period of cosmic history compared with the present day. That single fact changes the mood of the scene. The object is not merely far away in a static setting. It shines from a younger cosmos with different average conditions, different rates of growth, and a different balance between raw gas, star formation, and black hole activity. The record-breaking radiance seen from Earth is therefore inseparable from the ancient stage on which that radiance appears. Even the simple act of naming it the most powerful or most luminous object ever observed needs this historical setting. Observation does not mean greatest in all of reality. It means greatest among the objects whose light has reached human instruments and been measured. The universe may contain other sources beyond current reach, or sources hidden by time, orientation, or dust. What is known with confidence is that this quasar stands at the top of the present observational record for luminosity. That record comes from careful measurement of its spectrum, its brightness at different wavelengths, and the cosmological distance implied by its redshift. Once those are combined, the energy output inferred for the source becomes extraordinary, far beyond the combined starlight of an ordinary galaxy. Yet the measurement remains tied to the ancient epoch in which the light is emitted. The number does not float free from history. It is anchored in a universe that is still in one of its major growth phases. That youth can be described in simple physical terms. Space is smaller in scale, average matter density is higher, encounters between galaxies are more common than in the present era. Gas reservoirs are easier to find. Star-forming regions are widespread. Massive black holes, already built to astonishing sizes in some systems, can be supplied more effectively than many of their later counterparts. None of this means the entire universe is uniformly bright or unsettled. Vast dark intervals still separate luminous regions. Most of space remains extremely thin, but compared with the present cosmic age, the young universe is more favorable to rapid assembly and sustained feeding. A record quasar belongs naturally to such a setting. From Earth, the ancient light arrives as a narrow stream collected by mirrors, detectors, and spectra. In its own time, however, it leaves into a universe that has not yet spent most of its life. The Milky Way is not what it later becomes. The Sun does not exist. Earth does not exist. No observer waits beneath a night sky to receive the beam. The source shines anyway. It shines through an epoch rich in gas, young in structure, and still close enough to the great era of cosmic growth that the most luminous known quasar can emerge within it. The first region is therefore an age, not a place. It is the deep historical atmosphere around the object, the vast early condition that makes the existence of such radiance physically possible. Between the quasar and the later observer lies an enormous reach of expanding space. This region is so thin that ordinary language struggles to describe it without making it sound empty. Yet it is not a simple void. It is a broad interval through which light travels for more than 12 billion years while the universe itself changes scale. The main event in this region is not collision, turbulence, or impact. It is stretching. As the quasar's light moves outward, space expands, and the light wave is carried along with that expansion. Its wavelengths lengthen. Radiation that begins at shorter wavelengths arrives redder than it was when it left the source. This is cosmological redshift, the steady imprint of an expanding universe on a travelling beam of light. The greater the redshift, the longer the journey through expanding space has been. For J0529-4351, the measured redshift places the source at a very large distance and deep in cosmic history, showing that the light spends nearly all of the age of the mature universe in transit. This widening of the light does not mean that the quasar is simply throwing a beam across a fixed stage. The stage changes while the beam crosses it. That is the essential quiet drama of this second region. The the light leaves one universe and arrives in another. Not another universe in kind, but another in age and scale. By the time the radiation reaches Earth, space has expanded so much that the present-day separation between the source and the Milky Way is far larger than a simple 12 billion light-year picture would suggest. The travel time records one fact, while the continuing expansion of space records another. These two facts coexist without contradiction. One describes how long the light has been on the way. The other describes how much the universe has grown while the light travels. The beam therefore serves as a moving record of expansion itself, a physical thread connecting an earlier cosmic scale to a later one. Across most of this distance, the light passes through space that is almost unimaginably sparse. The atoms between galaxies are spread so thinly that even the best vacuum made on Earth would seem crowded by comparison. Yet this thinness still matters. Intergalactic space contains gas, mostly hydrogen with some helium and traces of heavier elements added over cosmic time. It also contains radiation fields, magnetic structure on large scales, and the gravitational influence of matter spread across the universe. The light from the quasar does not usually strike dense obstacles in this region, but it does move through a medium that can leave faint marks on the spectrum. When astronomers spread the light into its component wavelengths, narrow absorption features can appear where intervening gas has removed specific colors. These marks do not overpower the quasar's signal. Instead, they act as delicate notches, showing that the space between galaxies, though extremely thin, is real and physically active. Because the light travels for so long, even the rhythm of the quasar's changes is affected by expansion. Time intervals associated with the distant source appear stretched when measured at Earth. Variability that unfolds in the quasar's own frame is observed more slowly after crossing the expanding universe. This effect is subtle beside the overwhelming fact of the object's brightness, but it belongs to the same principle as the redshift itself. Expansion stretches wavelengths and also stretches the observed spacing of events carried by the light. In this region, then, space is not a passive separation. It alters the message while still preserving it. The quasar remains recognizable as a quasar. Its spectral lines remain measurable. Its luminosity can still be inferred. Yet everything arrives translated by the long growth of the universe through which the radiation has passed. The path is also shaped by geometry. Light does not travel through a universe arranged around human sightlines. It simply leaves the source in all directions, and only a minute fraction eventually reaches terrestrial instruments. For that fraction, the line of travel is remarkably clear. If a massive foreground galaxy lay directly across the path, gravity could split or magnify the image through lensing, making the quasar appear brighter than it truly is. This is an important concern for any exceptionally bright distant quasar. In the case of J0529-4351, the Discovery team examines that possibility and reports that the source does not show the separated multiple images expected from strong lensing in available observations. The brightness is therefore treated as intrinsic, rather than as a dramatic illusion created by a foreground lens. That result makes the expanding path between source and observer even more striking, because it means the vast brightness survives the long journey without depending on large gravitational amplification along the way. Even so, the light does not cross a perfectly featureless interval. Over billions of years, it moves through regions of slightly different density, through broad washes of tenuous gas, and through the changing radiation environment of a universe that matures as the beam advances. Some wavelengths are absorbed more easily than others by intervening material. Some are shifted out of visible range and into the infrared by the time they arrive. This is why distant ancient objects often require infrared-sensitive instruments for clear study. Light that begins in ultraviolet or visible bands can be shifted to much longer wavelengths before detection. The object itself does not need to change its nature for this to happen. The journey alone is enough. The expanding space between quasar and observer acts as a slow filter and translator, moving the signal into new wavelength ranges while preserving the evidence needed to identify the source and estimate its distance. There is a calm impersonality to this region. It does not care that the light it carries comes from the most luminous known object. Expansion treats every long-travelling wave by the same rule. The same broad principle that shifts the light of ordinary galaxies also stretches the emission of this extreme quasar. What changes is scale. The journey is longer, the redshift greater, the required instruments more sensitive, and the inferred luminosity more astonishing. Yet the mechanism remains the same. Space grows, wavelengths lengthen. Ancient light arrives older in every meaningful observational sense. By the time the beam reaches Earth, it has crossed not merely distance, but the history of expansion itself. This second region is therefore a long corridor of transformation without violence, a widening interval in which the universe leaves its signature on the travelling light before any nearer structure around the quasar needs to be considered. Around the long path of expanding space, the universe is not arranged at random. On the largest scales, matter gathers into a pattern called the cosmic web. This pattern is made of filaments, sheets, and dense knots separated by enormous low-density regions. Dark matter provides most of the framework, while ordinary matter follows that framework and collects along the same general lanes. Galaxies do not appear evenly scattered. They tend to occupy these link structures, with the richest systems found where several filaments meet. In this region around the quasar, the subject is not yet a single galaxy or halo, but the wider province of large-scale structure in which such a source is most likely embedded. NASA and ESA descriptions of the cosmic web present it as the skeleton of the universe, the network on which later galaxies, groups, and clusters assemble. This web grows from tiny early differences in density. Regions that begin only slightly denser than average exert slightly stronger gravity, and over time they attract more matter. The richer regions grow richer, while the emptier regions lose relative importance. The result is not a smooth fog but a connected pattern, with matter moving along preferred directions toward denser intersections. In this sense, the cosmic web is a map of where gravity has done more work and where it has done less. The quasar belongs to one of the brightest and most massive kinds of galactic centers, so its outer environment is naturally considered in relation to these denser lanes of the web rather than to the emptiest cosmic expanses. The contrast between these regions is important. A cosmic void can span immense distances while containing very little material compared with the cosmic average. A filament, by contrast, is still thin on human scales but rich on cosmological scales, because it channels matter across long distances and connects one concentration of galaxies to another. The knots where filaments meet are the most valuable addresses in this geography. They are places where gravity gathers traffic from several directions at once. A quasar as luminous as this one is naturally imagined within that busier kind of province, not out in the loneliest reaches between structures. Observations of other distant luminous quasars support this picture. In some cases, astronomers find that a powerful quasar lies within or beside a crowded young structure, with several galaxies collecting in the same neighborhood. Web observations reported by ESA describe a massive forming cluster around an early red quasar. and NASA has highlighted a 3 million light-year filament of galaxies anchored by a luminous distant quasar. These examples do not prove that every extreme quasar occupies the same kind of province, but they show that quasars can mark dense knots and growing filaments in the early universe. They are often not isolated lanterns placed in featureless dark. The evidence is useful, but it does not remove all uncertainty. Studies of quasar clustering show that luminous quasars tend to be associated with massive dark matter environments. Yet the exact strength of that association is still studied. One analysis of quasars at a redshift near 4 finds no clear luminosity dependence in clustering across its sample, while also noting that luminous quasar activity is expected in very massive halos in the early universe. This balance matters here. It allows the region around the record quasar to be described as a likely dense province of the cosmic web, without pretending that astronomers have already drawn every surrounding filament in detail. Observations indicate a preference for rich environments. It remains uncertain how unusual the larger neighbourhood of this specific source is beyond the source itself. Even without a full map of the exact neighbourhood of J0529-4351, the logic of the cosmic web helps explain why such a source can exist. The most luminous known quasar requires immense and sustained access to matter. On the widest scales, that access begins with location. A galaxy placed in a poor, thin region of the web has less opportunity to receive fresh inflow than one placed where filaments converge and matter is guided inward by gravity. The outer province does not feed the black hole directly in a simple straight line, but it sets the long-term availability of mass. Filaments act as supply corridors, dense intersections act as gathering grounds. The quasar's brightness therefore suggests not merely an extreme centre, but a favourable large-scale address within the architecture of the universe. This province is quiet in appearance. No observer within it would see glowing ropes stretched across the sky. Much of the web is revealed only through surveys, simulations, absorption studies, and careful measurements of gas and galaxy positions. NASA visualizations show galaxies as bright knots, and the connecting material as strands that would not be obvious to the unaided eye. Some of the matter in these filaments is diffuse gas, some is dark matter detected only through gravity, and some is gathered into galaxies whose light outlines the underlying pattern. The region therefore has a hidden quality. It is structurally strong but visually faint, more like a gravitational landscape than a bright object. There is another reason this outer pattern matters. A Nature report from observations around a luminous high redshift quasar describes a cosmic web filament seen in Lyman alpha emission, extending for about 460 physical kiloparsecs. In cases like that, the quasar does more than occupy a dense region. Its radiation helps illuminate gas that would otherwise remain almost invisible. The source and the web become linked in two ways at once. The web helps make the quasar possible by concentrating matter, and the quasar helps reveal parts of the web by lighting surrounding gas. This makes the large-scale environment around a luminous quasar more than background scenery. It becomes a physically connected outer layer of the same system. For J0529-4351, the discovery paper establishes the extraordinary luminosity and distance of the quasar itself, while the broader cosmic web setting is inferred mainly from what is known about structure formation and the environments of other powerful quasars. That is enough to define the present region with care. The object does not float in meaningless emptiness. It occupies a province shaped by the universe's largest gravitational pattern, a terrain of filaments and nodes where matter has been gathering for a long time before the light begins its journey. In this third region, the quasar is still only a point within a much wider architecture. Beyond the visible body of the quasar's host system lies a much larger gravitational domain, the dark matter halo. This region does not shine, reflect, or absorb light in any direct way that telescopes can record as an image. It is inferred from gravity. NASA describes dark matter as the invisible glue that holds the universe together, and in galaxies it provides most of the mass that shapes the motions of stars, gas, and satellites. In the broad picture of cosmic structure, cold dark matter forms halos first, and those halos become the wells into which ordinary matter falls. The halo is therefore the first true local container around the quasar system, larger than the visible galaxy and quieter than anything that later happens in the bright nucleus. It is the deep bowl of gravity within which all the inner regions are arranged. A halo is not a shell with a hard surface. It is a vast, roughly rounded distribution of unseen mass, whose density is highest toward the center and falls outward with distance. Its outer edge is not like the wall of a room. It is better understood as the scale over which the system remains gravitationally bound and distinct from the average cosmic background. Ordinary matter responds to this hidden structure. Gas drifting through the cosmic web slows and settles when it enters the halo's pull. Smaller galaxies may be captured by it. The visible galaxy that later appears at the center is only the condensed luminous part of a much larger, darker arrangement. In that sense, the quasar does not begin with light. It begins with gravity. For a quasar this luminous, astronomers generally expect a very massive halo. The exact value for J0529-4351 is not yet directly measured in the way its brightness and redshift are measured, so caution is necessary. Observations of quasar clustering, however, give a consistent guide. A well-known clustering study at moderate redshift found typical quasar halo masses near 3 trillion solar masses, while more recent work extending to much earlier cosmic times reports that quasars continue to occupy large halos and may activate at a characteristic halo mass across redshift. A recent high redshift clustering analysis using JWS, T-based quasar galaxy environments, similarly concludes that quasars at very early times reside on average in massive halos. These results do not identify the precise halo of this record source, but they support the picture of a substantial dark domain capable of sustaining a rare and powerful quasar. That mass matters because a halo is more than a container. It regulates supply. The depth of the gravitational well influences how much gas can be retained, how effectively inflowing material can be slowed, and how resistant the system is to losing matter back to intergalactic space. A shallow halo can be disturbed more easily. Gas heated by stars or by an active nucleus can escape more readily. A massive halo, by contrast, keeps a firmer hold and preserves a reservoir from which the inner galaxy can continue drawing. This does not guarantee that the central black hole will become extraordinary. Many massive halos do not host record quasars, but an extreme quasar is unlikely to arise without a strongly favourable gravitational foundation beneath it. The halo also acts as a mediator between the cosmic web and the central system. In the previous region, filaments and large-scale structure direct matter toward dense intersections. Here that matter first becomes locally claimed. Once gas and smaller systems enter the halo, they no longer belong only to the web in a broad statistical sense. They move within the gravity of one dominant structure. Their paths are bent toward the center. Their speeds, temperatures, and later histories are affected by the halo mass. The dark halo therefore translates large-scale cosmic geography into local conditions. It takes the broad supply lines of the universe and turns them into a bounded environment. There is also a timescale hidden in this region. Halos grow by merger and accretion over long stretches of cosmic history. Small dark clumps merge into larger ones, and large halos continue to gain mass from surrounding space. NASA descriptions of cold dark matter formation emphasize this bottom-up pattern, in which smaller structures assemble first and then build larger systems. By the epoch of J0529-4351, enough time has passed for some halos to become enormous, but not enough for the universe to have exhausted its supply of easy inflow. This combination is important. The halo can already be deep and mature in its gravitational influence, while the wider environment still remains rich in available gas. Although dark matter dominates the halo's mass, the halo is not empty of ordinary matter. Gas can fill much of the volume in thin, hot, diffuse form. Some of it cools over time, some remain suspended at high temperature, some streams inward along denser channels. In many systems, this gas is difficult to observe directly, especially at great distance. But its presence is physically expected because ordinary matter falls into the same gravitational wells as dark matter. The dark and visible components are not mixed in equal ways or with equal concentration, yet they are linked. The halo sets the gravitational frame, and the gas responds within it. For J0529-4351, the discovery paper emphasizes the observed luminosity and the enormous black hole mass inferred from the accretion disk. Not a direct halo measurement. That distinction should remain clear. Observations indicate that very luminous quasars generally reside in massive halos, and theory expects strong black hole growth to be favored in deep gravitational wells. It remains uncertain exactly how exceptional the host halo of this specific quasar is compared with other luminous quasars of similar epoch. Still, the outer dark domain can be described with confidence in broad terms. It is large, dominant in mass, invisible in light, and essential in function. Before the galaxy appears as a visible body, this quiet halo already surrounds the whole system and gives the most powerful known quasar a place to exist. At the center of this dark halo sits the visible galaxy that contains the quasar. It is the larger body of stars, gas, and dust gathered by gravity into a galactic system, even if that system is hard to see clearly. A quasar is not a separate object living outside a galaxy. NASA defines it as an active galactic nucleus, an extremely bright core caused by matter falling toward a supermassive black hole. ESA describes the same phenomenon as a compact central region so luminous that it can outshine the rest of the galaxy altogether. The host galaxy is therefore always present around the glare, even when the nucleus dominates the view. In physical terms, the quasar is the active center, while the galaxy is the broader home that gives the center a place, a population of stars, and a reservoir of ordinary matter. In a nearby galaxy, the main envelope is easy to imagine. There may be a disk, a bulge, spiral arms, or a more rounded elliptical form. In a distant quasar host, that outline becomes much harder to recover because the nucleus appears nearly point-like, and much brighter than the surrounding stars. NASA notes that quasars are often much brighter than the galaxies around them, making the host light difficult to separate from the light of the central source. Independent JWST-related work makes the same practical point, stating that a quasar can outshine the combined starlight of its host by several times. In this region, then, the galaxy is physically large but visually subdued. For J0529-4351, present observations do not yet provide a fully resolved portrait of the host galaxy itself. The discovery paper concentrates on the quasar spectrum, its extreme luminosity, and the mass of the central black hole inferred from the accretion disk. When it turns to the host galaxy, The paper speaks of future observations of the host gas and motions with ALMA. That distinction matters. It means the host can be described confidently as the surrounding stellar system, but many visible details remain uncertain for this specific object. It remains uncertain whether the broad form is mainly disk-like, elliptical, strongly disturbed by interaction, or shaped by several processes at once. Even with those limits, the host galaxy can still be described in broad scientific terms. It is a full galaxy, not a small shell built only for the nucleus. Its stars extend across a region many thousands of light-years wide. Its interstellar medium, the gas and dust between stars, provides the material from which new stars can form and from which the center can draw energy-bearing matter. NASA material prepared for Webb observations of early quasars describes host galaxy studies in terms of measuring stars, composition, and galactic structure. ESA reports on another powerful early quasar similarly discuss gas, dust, and stellar material within the host galaxy itself. These observations support a restrained but clear picture of the host envelope as an ordinary Galaxian substance, even if extraordinary in activity. The stars are the most stable visible part of that envelope. They make the host into a galaxy rather than a loose cloud around an active core. Billions of stars may occupy the system, moving under the combined pull of dark matter, gas, and the central mass concentration. Yet in a bright quasar host, these stars lose the contest for attention. The central nucleus can dominate the visible output even though it occupies only a tiny inner region compared with the size of the whole galaxy. NASA's Quasar Overview states that quasars are the most powerful type of active galactic nucleus, and ESA notes that such nuclei can outshine the rest of their galaxies altogether. This mismatch between physical scale and visual dominance is one of the defining features of the host envelope. Dust also belongs to this galactic body. In astronomy, dust means tiny solid grains mixed with gas between the stars. It dims, reddens, and reprocesses light. In active galaxies, it helps determine what can be seen directly and what must be inferred through infrared observations. NASA explains that infrared observations are especially useful because they help astronomers peer through the gas and dust in galactic centers, and for distant quasars, they're even more important because cosmic expansion shifts much of the emitted light into the infrared by the time it reaches Earth. The host galaxy envelope is therefore not best imagined as a clean, transparent system. It contains obscuring and glowing material throughout its visible body, especially toward the inner regions where activity is strongest. Its overall shape may preserve signs of how the galaxy has grown. Hubble studies of quasar homes show diversity. Some host galaxies appear disturbed or interacting, while others look comparatively undisturbed. NASA summarizes that most quasars lie at the cores of luminous galaxies, and that interactions between galaxies can help turn quasar activity on, though some systems show no obvious violent trigger. That balance is important for J0529-4351 because it prevents the host from being forced into one dramatic picture without evidence. It may belong to a system influenced by merger-driven growth, or to a massive galaxy whose central activity is sustained by quieter transport of gas. Observations of quasars as a class indicate that both routes are possible. Because J0529-4351 shines from a young cosmic epoch, its host galaxy is also being viewed at an earlier stage of galactic history than a nearby quasar host seen today. Webb observing programs aimed at early quasars are designed precisely to measure the stars and composition of host galaxies in order to understand how black holes and galaxies grow together. For this record source, the exact appearance of the host remains partly hidden by the central brilliance. Still, the core scientific picture is firm. The most powerful object yet observed is not an isolated point in darkness. It is the blazing nucleus of a galaxy, enclosed by a larger stellar body whose ordinary materials of stars, dust, and gas surround an extraordinary centre. Around the visible body of the host galaxy lies a wider and thinner envelope of gas known as the circumgalactic medium. This term means the gas surrounding a galaxy but still belonging to its gravitational domain, neither fully part of the bright stellar body nor fully part of the broader intergalactic space beyond. It is not a smooth shell and not a neat boundary. It is an extended, uneven reservoir spread through the outer reaches of the galactic environment, held inside the dark halo and shaped by gravity, heating, cooling, and long cycles of motion. In this region, the quasar is still far inside, hidden by distance and by layers yet to come. What matters here is the large store of ordinary matter surrounding the galaxy, the quiet envelope from which later activity can draw. This gas is extremely thin by ordinary standards, yet on galactic scales it contains a great deal of mass. Much of the ordinary matter associated with galaxies is thought to spend long periods in this outer medium rather than inside stars. Astronomers sometimes describe it as part of the missing ordinary matter problem, because the amount of ordinary matter expected from cosmology does not all appear inside stars and cold gas within galaxies. A significant fraction lies in diffuse, difficult-to-detect form around galaxies. The circumgalactic medium is therefore not a minor fringe. It is one of the main places where a galaxy keeps its accessible matter. It surrounds the stellar body like a broad invisible sea, sparse in density but vast in extent. Its structure is layered in temperature rather than in sharply separated shells. Some of the gas is hot, heated to very high temperatures by gravitational collapse, shock heating, and energetic processes within the galaxy. Some is warm and ionized, meaning its atoms have lost electrons under strong radiation or collisions. Some is cooler and denser, gathered into clouds or filaments that can survive for a time inside the hotter environment. Because these forms coexist, astronomers call the circumgalactic medium multiphase, a simple way of saying that it contains gas in several physical states at once. It is not still. It churns, mixes, cools, heats, and changes ionization state while remaining spread across a large volume. The gas also carries a record of the galaxy's past. Some of it is relatively pristine, meaning it has not been heavily enriched by many generations of stars. Some of it contains heavier elements produced inside stars and later expelled outward. In astronomy, these heavier elements are often called metals, even when they include oxygen, carbon, or silicon. Their presence in the circumgalactic medium shows that galaxies do not keep all of their processed material locked inside stars or within the bright inner body. Over time, star formation and central activity push enriched gas outward. The outer envelope thus becomes both a storage region and an archive. It preserves traces of what the galaxy has made and what it has lost. This region is difficult to observe directly because it emits little light of its own. Much of what is known comes from absorption, when the gas reveals itself by removing narrow parts of the light from bright background sources. A distant quasar shining through the outer envelope of another galaxy can expose the gas by these faint spectral marks. In other cases, telescopes detect ultraviolet, infrared, or X-ray signatures from parts of the medium, especially when the gas is hot or when it is illuminated in particular ways. The picture that emerges is one of complexity rather than simplicity. The circumgalactic medium is clumpy in some places, smooth in others, rich in long-lived hot gas and scattered with cooler, denser structures moving through it. For a galaxy hosting an extreme quasar, this reservoir becomes especially important. A source as luminous as J0529-4351 cannot rely only on the gas already settled deep in the center. On long timescales, the broader galaxy must be supplied. And beyond the galaxy, the circumgalactic medium acts as the nearest large reserve. It does not feed the quasar in a direct straight descent. The gas can remain suspended in the outer halo for long periods, circulating, cooling, or being stirred by energy from the galaxy. Even so, this is the region where much of the future supply exists before it ever becomes part of the denser inner system. It is the outer pantry of the galaxy, broad, faint, and essential. The circumgalactic medium is also a zone of exchange. Gas does not only wait there in stillness. Some material arrives from beyond, entering the halo from the larger cosmic environment. Some departs from the galaxy itself, driven outward by supernova activity, stellar winds, and active galactic processes. Some falls back after earlier ejection, joining a long cycle of recycling. This makes the region neither purely inflowing nor purely outflowing. It is an intermediate domain where matter can pause, mix, and change condition before continuing in one direction or another. The galaxy and its surroundings remain connected through this gas at all times. Because the quasar host lies in the young universe, that exchange may be especially rich. Galaxies at earlier cosmic times often have greater access to fresh gas, and their outer reservoirs may be more active as they build mass and form stars. Still, caution is needed for this specific source. The extraordinary brightness of J0529-4351 is well measured, but the exact mass, shape, and physical state of its circumgalactic reservoir are not yet mapped in full detail. Observations indicate that quasars and massive galaxies generally live inside extensive gaseous halos, and future observations can clarify the gas content and motions around this one. For now, the broad scientific picture is secure even where the local details remain uncertain. This outer reservoir is not dramatic to the eye. It would not appear as a bright ring around the galaxy. Most of it would remain unseen without sensitive instruments and careful analysis. Yet its quietness is deceptive. Here the galaxy keeps much of its ordinary matter outside the stars. Here gas absorbs radiation, stores heat, carries metals, and waits in unstable balance between escape and return. Here the boundary between galaxy and surrounding universe becomes blurred, because the circumgalactic medium belongs to both histories at once. It is shaped by what enters from outside, and by what the galaxy sends outward. In this sixth region, the story remains broad and patient. The host galaxy sits at the center, but the main subject is the vast envelope just beyond its visible edge. It is diffuse, multiphase, chemically mixed, and gravitationally bound. It surrounds the galaxy not as decoration but as one of its most important material domains. Before matter moves through the more crowded inner roots, before it settles into denser structures, it exists here in the outer gas reservoir, spread through the circumgalactic medium like a hidden ocean around the most luminous known quasar. Inside the wider gas reservoir, matter begins a slower and more difficult journey through the inner body of the galaxy. This region is defined not by one object but by a process. Gas that is spread across galactic scales cannot simply fall straight to the center. The main obstacle is angular momentum, the tendency of orbiting material to keep moving around the center rather than directly inward. For gas to travel deeper into the galaxy, that angular momentum must be reduced or redistributed. Astronomers describe this as transport. The phrase sounds abstract, but the meaning is simple. the gas must lose some of its orderly orbital motion so that gravity can pull it closer to the middle. In this section, the host galaxy becomes a place of slow rearrangement, where broad orbits are gradually turned into inward drift. Studies of active galactic nuclei describe this transport of gas across many scales as one of the central problems of black hole fueling, and they identify angular momentum loss as the key requirement. The galaxy does not remove angular momentum by magic, it uses structure. If the stellar body has a bar, an elongated concentration of stars across the inner galaxy, that bar can exert gravitational torques on the gas. A torque is a twisting force that changes rotational motion. Under such forces, gas clouds can no longer follow perfectly circular paths. They collide, shock, compress, and move along lanes where angular momentum is exchanged. NASA-supported work on barred galaxies notes that bars drive inflow and can contribute to the growth of central stellar components and black holes. Observational studies of active galaxies similarly describe clear connections between larger bars or spiral structures and dust spirals on smaller inner scales, indicating that the galaxy's visible form can help channel gas inward. The route is not a straight tunnel. It is more like a sequence of distorted paths in which the gas repeatedly gives up a little of its ordered motion and settles to smaller radii. Spiral structure can perform a similar task. In a rotating galaxy, gas may collect along curved lanes where the gravitational pattern is not perfectly symmetric. These asymmetries matter because a perfectly smooth and symmetric galaxy would allow gas to circle for very long periods without moving far inward. Once asymmetry appears, the balance changes. Tangential forces arise. Clouds cross paths more often. Compression builds along dust lanes and spiral arms. Some of the gas is converted into stars along the way, but some continues inward after collisions and shocks remove energy from its motion. Reviews of fueling in active galaxies describe bars, spirals, and other non-axis symmetric features as the main means by which gas can be driven toward the center from galactic scales. The inner galaxy thus acts less like a calm disk and more like a set of guiding distortions, using its own uneven gravity to encourage inward movement. Interactions and mergers can strengthen this process, though they're not required in every case. When galaxies pass near one another or combine, their gravitational fields disturb gas on large scales. The result can be stronger torques, more inflow, and a greater supply to the inner galaxy. Older NASA literature on nuclear activity identifies interactions as one route by which distortions are induced, and radial inflow becomes easier. More recent work adds caution by showing that not every active nucleus is strongly linked to a recent interaction, especially when looking across broad samples. This balance is important for the present source. J0529-4351 may live in a system shaped by interactions, or it may be fueled largely by internal structure within a massive gas-rich galaxy. The general picture is secure even where the specific trigger remains uncertain. In either case, the inner galactic inflow depends on the same physical need. Gas must be disturbed enough to give up angular momentum and move deeper into the central potential. The journey inward is not smooth or constant. Gas often stalls at particular radii. It can gather in rings, linger in orbiting concentrations, or be redirected into temporary patterns that slow further movement. NASA-linked studies of nuclear rings note that bar-driven inflow can pile gas up at contact points and resonant locations instead of letting it proceed freely. This means the inner galaxy is full of delays. Fueling a powerful nucleus is not simply a matter of having gas available somewhere in the host. The host must also keep breaking these temporary barriers, fresh torques, cloud-cloud collisions, magnetic forces, turbulence, and self-gravity all help move material onward. Some gas forms stars before it can go farther. Some is pushed back outward by local feedback. Some remains in dense lanes and continues drifting inward over long times. The process is therefore irregular and layered, with many partial successes and many pauses. For a quasar as luminous as this one, the required inflow over long periods must be substantial. The discovery paper for J0529-4351 infers an enormous accretion rate at the centre, meaning that the host galaxy must ultimately provide a sustained supply chain from larger scales inward. This does not mean the whole galaxy is collapsing at once. It means that somewhere within the inner galaxy, enough gas repeatedly finds ways to lose angular momentum and continue descending. The galaxy therefore functions as a transport network. Outer reservoirs provide mass, while inner structures decide how much of that mass reaches smaller scales. The host does not merely contain the quasar, it actively prepares the fuel, sorting, compressing, and redirecting gas so that some fraction of the wider supply can proceed inward. This region is also one of competition. Gas moving through the inner galaxy is useful to more than one process. Star formation draws from it. Turbulence stirs it. Heating can puff it up. Outflows from earlier activity can disrupt it. The central engine may depend on the same gas that the galaxy uses to build new stars. As a result, the inner inflow is never perfectly efficient. Much of the material that enters the inner galaxy will not reach the deepest regions. It will cool and fragment into molecular clouds, collapse into stars, or be recycled into another orbit. Only a fraction continues its inward path. Yet because the galaxy is large and the available mass can be great, even a modest fraction may be enough to sustain strong nuclear activity if the delivery persists long enough. This is one reason why the quiet mechanics of the inner galaxy matter so much. Small changes in transport efficiency can decide whether a central black hole remains dim or becomes one of the brightest objects in the observable universe. In this seventh region, the story remains outside the nucleus itself. The main subject is the inward migration of gas through the host galaxy. From broad galactic motion toward the crowded central parts, gravity provides the destination, but structure provides the route. Bars twist, spirals compress, clouds collide, rings delay, and repeated losses of angular momentum let matter settle closer to the middle. The region is not violent in a single dramatic sense. It is persistent. Over long periods, these small rearrangements accomplish something immense. They take diffuse material from the living body of the galaxy and turn part of it into a directed inward flow. That slow transport through the inner galaxy is the last broad passage before the matter becomes part of the denser central environment surrounding the active nucleus. Within the inner reaches of the host galaxy, the environment becomes more crowded and more complex. This is the nuclear star region, the dense central neighborhood of stars, gas, and dust that surrounds the active nucleus before the quasar's own immediate structures take over. In an ordinary galaxy, the nucleus is simply a dense core of stars surrounded by more stars and gas. In an active galaxy, that same central district becomes far brighter and more disturbed because a supermassive black hole at the center is actively consuming surrounding matter. NASA describes active galactic nuclei as active supermassive black holes at the centers of galaxies, while its educational material notes that a normal galaxy core is a dense concentration of stars. These two facts meet in this region. The black hole sits at the center, but around it lies a broader inner city of ordinary galactic material that remains part of the host rather than part of the accretion flow itself. This central neighborhood is compact compared with the galaxy as a whole, Yet large compared with the immediate quasar engine, it may span hundreds to a few thousand light-years, depending on how the inner structures are arranged. Here the stellar density rises. Orbits become more crowded. Gas lanes that have drifted inward from the larger galaxy begin to intersect, compress, and pile up. Dust becomes more concentrated. The radiation field strengthens as the distance to the active center decreases. NASA's Webb explainer notes that infrared observations are essential for peering through the gas and dust-clogging galaxy centers, where much of the action is taking place. That phrasing captures the physical character of this region well. It is not a clean stellar bulge alone. It is a busy inner environment where stars, dust, and gas coexist under stronger gravity and in stronger light than in the wider body of the host galaxy. The stars in this region are not all of one age. Some belong to an older central population, long settled into the galaxy's inner structure. Others may form more recently when inward-moving gas becomes dense enough to collapse. In many active galaxies, astronomers find circumnuclear star formation, meaning star formation in the region around the active nucleus, rather than in the nucleus itself. ESA describes NGC 7469 as an active galactic nucleus surrounded by a starburst ring at a distance of about 1,500 light-years, with Webb revealing very young star-forming clusters and warm, turbulent molecular gas in between. This nearby example does not mean every active galaxy has the same ring, but it shows that the nuclear star region can be both old and newly renewed at once. It can hold mature stars, fresh stellar clusters, dusty gas, and signs that the active center is already reshaping the local interstellar medium. Gas in this region behaves differently from gas farther out in the galaxy. The volume is smaller, the crossing times are shorter, and collisions and shocks matter more. Molecular gas, the cool dense gas from which stars can form, may gather in arcs, clumps, spirals, or compact rings. Some of it remains relatively cool. Some is heated into warmer turbulent phases. Some becomes ionized by the nucleus, meaning its atoms are stripped of electrons by radiation or energetic collisions. A recent review of active galactic nucleus feedback emphasizes that active nuclei can alter the kinematics, distribution, and ionization state of multiphase gas. In simple terms, the gas near the center can be moved, heated, rearranged, and chemically excited by the energy of the active source. The nuclear star region is therefore not just a waiting room for inward-flowing matter. It is a responsive medium that changes condition as the quasar shines. This environment is also one of competition. Dense gas that reaches the nuclear region does not belong exclusively to the black hole. Some of it forms stars, some of it stays in clouds or filaments, some of it is stirred into turbulence and resists immediate collapse. Some is pushed aside or heated by radiation and winds from the active center. NASA notes that jets and winds from active galactic nuclei can heat gas and influence star formation in their host galaxies. ESA's Webb view of NGC 7469 adds direct evidence that small dust grains can be destroyed within a few hundred light-years of the nucleus, and that the active center affects the surrounding interstellar medium. This means the nuclear star region is balanced between creation and disruption. It can build new stars while also being eroded, heated, or chemically altered by the central activity. The gravity of the region has its own layered character. The host galaxy still contributes most of the overall gravitational setting on these scales, but the central mass concentration becomes increasingly important inward. Stars in the nuclear region orbit through a changing landscape shaped by the galaxy's bulge. The dark matter background, dense gas concentrations, and the growing influence of the central black hole. Even before the black hole's gravity fully dominates the motion of nearby matter, its presence helps organize the inner neighborhood. The result is a region that is neither simply part of the broad galaxy, nor yet part of the compact quasar engine. It is an intermediate central district where stellar crowding, gas accumulation, and rising radiation combine into a distinct environment. NASA's explainer on active nuclei stresses that for nearby active galaxies, astronomers can separate what happens near the active nucleus from what happens elsewhere in the host, and this region is exactly that separable inner neighborhood. For J0529-4351, the existence of such a nuclear star region is physically expected because quasars are active galactic nuclei embedded in galaxies, but its detailed appearance is not yet directly mapped. The quasar is so distant and so bright that the host galaxy and its central stellar environment are difficult to isolate. The discovery paper focuses on the luminosity, accretion disk, and black hole mass, while noting that future ALMA observations could measure the mass and motions of gas in the host galaxy. That makes the present region partly general and partly specific. The general physics is well established from active galaxies studied in greater detail nearby. The exact arrangement of stars, dust, rings, clumps, and warm molecular gas around this particular quasar remains uncertain. Even with that uncertainty, the scientific picture remains clear. Before reaching the quasar's own emission zones, matter enters a crowded central neighborhood where the host galaxy is at its most concentrated. Stars gather densely, dust veils parts of the scene. Gas arrives, stalls, fragments, forms clusters, and becomes turbulent under the pressure of radiation and motion. Some of that gas will never go farther inward. Some will become stars and remain part of the nuclear stellar population. Some will be heated or displaced by the activity at the center. This region is therefore both a barrier and a nursery, both a congested hub and a living inner ecosystem. It surrounds the quasar not as a decorative frame but as the dense central society of ordinary galactic matter within which the extraordinary nucleus continues to shine. Beyond the crowded nuclear star region lies a larger and thinner zone of gas that glows under the power of the quasar. This is the narrow line gas shell, often called the narrow line region in astronomy. The name comes from the appearance of its light when spread into a spectrum. A spectrum is light separated by wavelength. In this region, the glowing gas produces bright emission lines that remain relatively narrow because the gas moves more slowly than gas much closer to the center. The clouds still travel at great speed by ordinary standards, but their motions are moderate compared with the most extreme inner gas. What matters here is not violent compact motion, but a broader illuminated shell, spread across a much larger volume around the nucleus. The gas in this region is ionized. Ionized gas means that atoms have lost one or more electrons, usually because they absorb energetic radiation. The quasar provides an intense flood of ultraviolet and X-ray light, and that radiation reaches outward into surrounding clouds. When the light strikes the gas, it changes the atoms and raises electrons to higher energy states. As the electrons settle back, they emit light at specific wavelengths. Each chemical element leaves its own pattern, so the shell becomes a glowing record of composition and physical condition. Oxygen, nitrogen, hydrogen, sulfur, neon, and other elements can all contribute to the line seen in active galaxies. The result is a region that does not shine by reflected light alone. It shines because its atoms are actively excited by the nucleus and then emit their own radiation. This shell is thin in density but large in size. It can extend across hundreds or even thousands of light years around an active nucleus, depending on the source and on how deeply observations can detect faint gas. The clouds do not form a smooth, perfect sphere. They often appear in clumps, arcs, cones, filaments, or uneven patches, shaped by the structure of the host galaxy and by the direction in which radiation escapes most easily. Even so, taken as a whole, the narrow-line gas forms a distinct outer luminous zone around the quasar. It is broad enough that the light crossing time of the region is long, and because of that size, its response to changes in the central source is slower and more average than in smaller inner zones. The gas does not flicker in immediate step with every change at the center. It preserves a calmer, more extended imprint of the quasar's radiation. Its spectrum reveals why astronomers treat it as a separate region. The emission lines are narrower because the gas velocities, while still high, are not dominated by the deepest gravitational motions. The line widths therefore become a clue to location. Wider lines usually mean faster motion and stronger velocity spread. Narrower lines point to a more extended and less extreme environment. In this shell, the gas still feels the influence of the nucleus, but it is no longer packed into the most compressed and rapidly moving domain. Its light is also valuable, because it can often be studied even when the central engine itself is too bright or too compact to resolve directly. The shell acts like a readable outer atmosphere of the active nucleus, carrying information about ionization, density, chemical enrichment, and the geometry of escaping radiation. The narrow-line gas shell also connects the quasar to the host galaxy. It belongs to the active nucleus in the sense that the nucleus powers its glow, yet it also belongs to the galaxy because the gas itself is part of the galactic environment. Some of the material may have been present in the central region before the quasar became strongly active. Some may have been rearranged, compressed, or pushed outward by previous activity. Some may mix with gas from star-forming regions or with gas already circulating through the central body of the galaxy. This makes the shell a meeting ground between nuclear power and ordinary galactic matter. The quasar writes energy into the gas, and the gas answers with light. Its chemical content matters, because the clouds contain elements forged in stars. They show that the host galaxy has already experienced a history of stellar birth and death. The shell is not made only of untouched primordial hydrogen and helium. It contains enriched material, evidence that earlier generations of stars have lived, produced heavier elements, and returned part of that material to the surrounding medium. In that sense, the narrow-line shell carries both the signature of the present quasar and the memory of the host galaxy's past. Light from the active center excites the gas in the present, while the elements inside the gas reveal the older life of the galaxy itself. This region can also show motion outward. In many active galaxies, narrow-line gas is not simply sitting in place. It can stream away from the nucleus in ionized outflows, pushed by radiation, winds, or pressure from the active center. These motions can shape the cloud geometry and shift the emission lines slightly from the wavelengths expected for still gas. Some clouds move toward the observer, some away, and some in more tangled patterns. Even so, the general character of the shell remains less extreme than the smaller central zones. It is a region of illuminated response and moderate outflow, not the deepest release of energy itself. The quasar's power becomes visible here as structure, ionization, and motion written across a wide volume of gas. Dust can coexist with parts of this shell, though dust survives unevenly depending on local temperature and radiation. Some regions may remain mixed with grains and denser clumps, while others are too harsh and ionized for dust to persist easily. This gives the shell a patchy appearance in physical terms. Radiation passes more freely through some directions and less freely through others. As a result, The glowing region is often anisotropic, meaning not the same in every direction. Its brightness and extension depend on where gas is present and where the quasar's light can reach it without being blocked or weakened too strongly. The shell therefore records both the source of illumination and the structure of the surrounding medium. For the record, quasar J 0529-4351, the exact shape and extent of this shell are not yet mapped in the direct detail available for much nearer active galaxies. The object is extremely distant, and the central source dominates the observation. Still, the existence of ionized narrow-line gas around a quasar is part of the standard physical picture of active galactic nuclei, and the spectrum of the source itself shows the line-emitting environment that surrounds the brilliant center. This allows the region to be described with confidence in broad scientific terms even where its detailed architecture remains uncertain. In this ninth region, the most powerful known quasar is no longer only a compact blaze hidden in distance. Its influence becomes legible across surrounding space. Thin clouds of gas absorb energetic light, become ionized, and emit narrow spectral lines that travel outward across the universe. The shell is extended, enriched, structured, and responsive. It glows not because it generates the power on its own, but because it receives the power and translates it into visible evidence. Across this wider gas zone, the quasar illuminates its own outer language, written in narrow lines through the ionized shell that surrounds the active heart of the galaxy. Inside the glowing narrow-line shell, the environment becomes thicker, warmer, and more obscured. This region is the dusty Taurus belt, a broad ring-like concentration of gas and dust surrounding the active center. In astronomy, a torus means a donut-like form, though in real galaxies the structure is not a smooth, perfect ring. It is better understood as a thick, uneven belt of material gathered around the nucleus, with a hollowed inner cavity and a great deal of clumping throughout its body. It lies close enough to the active center to be strongly heated, yet far enough away for solid dust grains to survive in much of the region. Here the quasar is no longer merely lighting distant gas. It is shaping a heavy belt of matter that absorbs, hides, and reprocesses its radiation. This region matters because dust changes what light can do. Dust grains are tiny solid particles made mostly of carbon-rich or silicate material. They are far smaller than grains of sand, yet numerous enough to control the appearance of many galactic environments. In the Taurus belt, dust absorbs shorter wavelength light from the nucleus, especially ultraviolet and visible radiation, and then re-radiates that energy as infrared light. The result is a warm, obscuring structure that does not simply block the center, it transforms the energy passing through it. Light that would otherwise leave the nucleus directly is intercepted, heated into the dust, and then released again at longer wavelengths. This makes the torus one of the main reasons active galactic nuclei can look so different from one line of sight to another while still being powered by similar central engines. The inner edge of the torus is set by heat, too close to the nucleus. The radiation is intense enough to destroy solid grains. Dust cannot survive where the temperature rises above the sublimation point, the point at which a solid turns directly into gas-like particles without first becoming liquid. This creates a dust-free inner cavity. Beyond that boundary, grains can exist, and the torus begins as a hot inner rim. Farther out, the temperature falls, and the dust becomes cooler. The structure is therefore layered by heat. The inner belt glows more strongly in the near and mid-infrared, while farther regions contribute cooler infrared emission. Even though the torus is not enormous on galactic scales, it contains a broad range of physical conditions compressed into a relatively compact space. The belt is also clumpy rather than smooth. This is one of the most important refinements in the modern understanding of active galactic nuclei. Earlier simplified pictures sometimes treated the torus as a dense uniform donut, but observations and modelling indicate that the material is broken into clouds, filaments, and irregular concentrations. Some lines of sight pass through many clouds and are strongly obscured. Others pass through fewer gaps and reveal more of the bright inner source. This helps explain why some active nuclei appear heavily hidden, while others appear more directly exposed. The difference is not always a change in the central engine itself. Often it is a difference in how the dusty belt lies along the line of sight, and how its clumpy structure distributes material around the centre. The torus is not only dusty, gas fills the region as well, mixed with the grains and moving in complex ways. Some gas is molecular, meaning it exists in bound combinations of atoms, rather than as isolated ionized particles. Molecular gas is important because it cools efficiently and helps maintain dense clouds. Some of the gas may be turbulent, stirred by collisions, radiation pressure, magnetic effects, and the gravity of the central mass. Some may orbit in a broadly ordered way, while some may rise and fall in a thicker puffed-up distribution. The torus belt is therefore both a structure and a circulation zone. It is not a static wall around the quasar. It is a living medium in motion, constantly heated, shadowed, mixed, and reshaped. Its thickness is part of its function. A thin, flat disk of dust would hide the centre only from a narrow range of viewing angles. A thick belt hides it from many more. This thickness may be supported by turbulence, radiation pressure, magnetic forces, or by material rising in outflows and falling back again. In simple terms, the torus stays puffed up because energy and motion keep it from collapsing into a razor-thin plane. The region is therefore vertically extended as well as radially broad. It wraps around the nucleus in three-dimensional form, creating a substantial zone of obscuration rather than a mere lane of dust. The infrared glow of the torus is one of the clearest signs of its presence, because the dust absorbs energetic radiation and re-radiates it thermally. The belt shines strongly in infrared wavelengths, even when it is hard to separate in direct images. This is especially important for distant quasars such as J 0529-4351. The source is so remote that the detailed architecture of the torus cannot yet be mapped in the same direct way achieved for some much nearer active galaxies. But the broad physics of quasar infrared emission and obscuring dust is well established. The torus is inferred not only from theory, but from the characteristic ways active nuclei shine across different wavelengths. The central engine produces the energy, and the dusty belt rewrites part of that energy into a warmer spectral form. This belt also marks a change in how the nucleus interacts with its surroundings. In the narrow line shell, the main effect is illumination of thin gas over large distances. In the torus, the main effect is interception. Matter is now dense enough and dusty enough to take in a large share of the outgoing radiation. Some directions remain relatively open, allowing radiation to escape more freely. Other directions are heavily shielded. The torus therefore gives the active nucleus an uneven interface with the rest of the galaxy. It determines which regions receive harsh direct light, and which remain partly protected behind dusty cover. In this way, the torus is both a barrier and a regulator. Its material may not remain permanently bound in a quiet orbit. Some current models and observations suggest that part of the obscuring structure is linked with dusty winds launched from the inner region, so that the torus may be partly a dynamic flow rather than a completely settled ring. Even so, from the scale considered here, it remains meaningful to describe the region as a belt, Whether its matter sits in thick clumps, circulates in turbulent orbit, or joins a slower dusty outflow, it still forms the major warm obscuring zone around the quasar. The exact balance between orbiting clouds and flowing material remains an active subject of research, but the broad picture is secure. For the most luminous known quasar, this region is likely under intense stress. The radiation field is enormous, heating is strong. Dust survival depends closely on distance from the center and on shielding within clouds. Yet the torus remains physically necessary as the main dusty interface between the brilliant nucleus and the broader galactic environment. It stores gas and grains, shapes the escaping light, glows in infrared warmth, and turns geometry into appearance. In this 10th region, the quasar is seen through a thick warm belt of obscuring matter, a dusty torus that surrounds the hidden center and quietly governs how the most powerful known object presents itself to the universe. Inside the dusty belt, the gas becomes denser, faster, and more directly exposed to the quasar's radiation. This is the broad-line cloud zone, commonly called the broad-line region. It is known mainly through its spectrum rather than through direct imaging. When the light of a quasar is spread by wavelength, some emission lines appear very wide. Those broad lines reveal gas moving at very high speeds, typically several thousand kilometers per second, far faster than the gas in the larger narrow-line shell. Reviews of active galactic nuclei describe this region as dense, photoionized gas close to the central engine, with motions that are predominantly Keplerian, meaning mainly controlled by orbit around the central mass, though traces of inflow and outflow are also present. The region is called a cloud zone because astronomers often describe its emitting material as clouds. But this word does not imply soft ordinary clouds like those in a planetary atmosphere. These are compact concentrations of gas moving through a severe environment of strong radiation and strong gravity. Their temperatures are high enough for efficient emission, and their densities are much greater than those of the larger ionized gas regions farther out. The gas shines because it is photoionized by the continuum radiation from the quasar. In simple terms, energetic light from the center strikes the gas, excites or strips electrons from atoms, and the atoms then emit the broad lines that make the region visible in spectra. The broadline region is therefore not seen as a glowing ring in ordinary images. It is inferred from the unusually wide spectral features that only fast, dense gas near the center can produce. Its size is small compared with a galaxy, but large compared with the black hole itself. Reverberation mapping, the study of delayed line response to changes in the continuum, shows that the broadline region has a measurable light travel size, and that the line-emitting gas does not sit at one single radius. Instead, it is stratified. High ionization lines tend to come from smaller radii, while lower ionization lines tend to arise farther out. This means the broadline cloud zone is layered within itself. It is not one thin shell. It is a thick and structured inner volume in which different atoms and ions radiate most strongly at different distances from the center. The same studies also support the view that the gas motions are largely gravitational, which is why line widths can be used, with caution, to estimate black hole masses. The transition from the dusty torus belt to this cloud zone is closely connected to dust survival. One review of broadline region formation states that the outer radius of the broadline region is set by dust sublimation in gas exposed to the central source. This means the broadline zone lives just inside the domain where dust can persist easily. In the torus, dust grains survive and absorb light. Here, much of that dust is gone, leaving gas that is more directly irradiated and more efficient at producing the characteristic broad emission lines. This creates a natural boundary between the warm obscuring belt and the faster line-emitting zone within it. The broad line region can therefore be understood as the first major dust-poor gaseous layer inside the torus, close enough to the quasar for dust to fail and for the gas to respond mainly through ionized emission. The shape of this region is still an area of active study. Reviews do not support a simple spherical cloud swarm. Instead, the evidence points toward a flattened or multi-component structure, possibly linked to the surface of the accretion disk and to disk-related winds. Peterson's review describes the current best evidence as favoring a multi-component line-emitting region with a disk-like structure and a disk wind as strong candidates for the origin of the broad emission. Another review states that the material is predominantly in Keplerian motion, but also shows traces of inflow and clear signatures of outflow. These descriptions matter because they show that the broadline cloud zone is not a static shell around the center. It is a dynamic inner atmosphere of the quasar, shaped by orbit, radiation, and likely vertical motion above the disk. Because the motions are so fast, the lines grow wide in the spectrum. A cloud moving toward the observer shifts its light slightly one way, while a cloud moving away shifts it the other way. When many clouds or emitting parcels of gas occupy different parts of the orbiting region, their light blends into a broad feature rather than a narrow one. The full width of such lines can exceed several thousand kilometers per second, and in luminous quasars the broad ultraviolet lines such as C4 and Mg2 are among the main tools used to characterize the region. In the discovery analysis of J0529-4351, the C4 and Mg2, broad emission line profiles are modeled with multiple broad Gaussian components, each defined as having a minimum full width at half maximum of 1000 km per second, clearly placing the source within the broadline quasar class. For this record quasar, the broadline cloud zone is expected to be exceptionally large. The discovery paper states that if J0529-4351 is not strongly lensed, its broadline region is expected to have the largest physical and angular diameter occurring in the universe among known quasars. By extrapolating the radius-luminosity relation, the authors predict an H-beta emitting broadline region radius of about 2.2 parsecs, with an angular diameter of about 0.64 milliarc seconds, larger in apparent size than the broadline region measured in the nearby quasar 3C 273. A later review of high redshift black hole mass estimates notes the same source as a promising case, because its expected broadline region size may be large enough for direct interferometric testing of these extrapolated relations. For the present script, this does not mean the broadline region has already been fully mapped. It means the source is so luminous that the standard scaling relations predict an unusually extended broadline zone. That combination of density, speed, and size gives the region a special role. It is one of the few inner layers through which astronomers can weigh the hidden black hole indirectly. If the gas is approximately virialized, meaning its motion is largely set by the gravitational field, then the size of the broadline region and the line width together provide an estimate of the central mass. For J0529-4351, the discovery paper explicitly uses the assumption that the broad emission line region represents virialized gas moving around the black hole as one route to estimating the black hole mass. The broadline cloud zone is therefore not just a decorative spectral feature, it is a measurable dynamical layer, one that carries information about gravity very close to the heart of the quasar. In this 11th region, the quasar is surrounded by dense, fast-moving gas that shines in broad emission lines and forms a structured inner volume just inside the dusty belt. The gas is highly irradiated, mostly dust-poor, stratified by ionization, and governed largely by the pull of the central mass. Its exact geometry remains uncertain, but observations indicate a flattened and dynamic zone with orbital motion at its core. Around the most luminous known quasar, this broad-line cloud region is expected to be the largest of its kind yet inferred, a vast inner field of rapid gas whose wide spectral lines reveal that the centre has drawn matter into one of the fastest and most luminous environments in the observable universe. Inside the broad-line cloud zone, the quasar does not only pull matter inward, it also drives matter outward. This region is the quasar wind layer, a fast outflowing domain launched from the active nucleus and pushed into the surrounding environment by the same energy that makes the source so luminous. Reviews of active galactic nuclei describe winds as one of the standard forms of nuclear output, alongside jets in some systems, and they note that outflows are commonly detected through blue shifted absorption lines in ultraviolet and X-ray spectra. A blue shift means that the absorbing gas is moving toward the observer along the line of sight, showing that the gas is leaving the nucleus rather than settling deeper into it. In this region, then, the quasar becomes not only a consumer of matter, but also a source of recoil, sending part of its energized gas back outward into the layered environment that surrounds it. These winds are not a gentle breeze. They can reach extraordinary speeds. Theoretical and observational reviews state that broad absorption lines in quasars are among the clearest signatures of such outflows, and that their velocities can reach a significant fraction of the speed of light, in some cases up to about 1/5 of that speed. X-ray observations reveal even more highly ionized ultrafast outflows with typical velocities around 1/10 of the speed of light, making them among the most energetic ionized winds known in quasars. Not every quasar shows every variety of wind, and the full geometry is often hidden because absorption depends strongly on viewing angle. Even so, the general picture is firm. The interactive nucleus launches gas fast enough that the outflow becomes one of the dominant ways in which the quasar communicates its power to the matter around it. The physical driver of the wind is still studied, and this uncertainty belongs naturally to the region. A concise theoretical review states that magnetic, radiation, and thermal driving likely all operate in active galactic nuclei, and that in many cases it is difficult to determine which one dominates. Radiation can push on ions and dust through light pressure, especially in very luminous quasars. Magnetic fields can fling gas outward along rotating field lines. Thermal heating can also lift gas from larger radii where escape is easier. These mechanisms may not be mutually exclusive. They can overlap in different parts of the flow or dominate under different conditions. Observations indicate that winds are real and often powerful. It remains uncertain in many individual systems exactly how the launch is partitioned among these driving processes. This layer is also likely to be structured rather than smooth. Reviews of quasar and active galactic nucleus outflows describe complex, inhomogeneous flows, with several absorbing components, uneven covering fractions, and a lack of simple spherical or axial symmetry. Some gas may rise in a wide equatorial wind, some may occupy narrower streams or clumps, some may be highly ionized and visible mainly in X-rays, while other parts are more easily traced in ultraviolet absorption. This means the quasar wind layer is not a perfect expanding shell. It is a dynamic zone of fast parcels, ionized phases, and changing lines of sight. The observer may intercept one part of the wind and miss another. Because of that, spectra reveal only a slice of the total structure, and different quasars can look very different even when outflows are broadly present in both. The wind layer matters because it carries momentum and energy away from the nucleus. A broad review of quasar feedback explains that warm ionized and cold molecular outflows driven by strong active galactic nucleus radiation fields or radiojets, can affect the surrounding host galaxy, a process often described as quasar-mode feedback. Another review notes that ionized outflows may quench star formation and active galactic nucleus activity if their kinetic luminosity reaches a modest fraction of the Eddington limit. In simple terms, the wind can become powerful enough to heat gas, sweep gas aside, or make further inward supply more difficult. The outflow is therefore not only a surface symptom of brightness, it is part of how the nucleus reshapes the regions around it. In this 12th layer, the quasar begins to push back against the very environment that feeds it. This outward push can also link the inner nuclear scales to the much larger host galaxy. Simulations of active galactic nucleus winds show that a fast nuclear wind can shock surrounding gas and generate larger-scale galactic outflows with lower speeds but much greater reach. Reviews of observations similarly connect nuclear ionized winds with broader disturbances in the host galaxy. The wind layer considered here is still close to the nucleus, but it is already the seed of later consequences. As the fast gas expands outward, it can collide with denser surrounding material, produce shocks, convert part of its kinetic power into heat, and transfer momentum into clouds and interstellar gas. The local outflow thus becomes a messenger that carries central power outward across many scales. For J0529-4351, the direct discovery paper does not report a mapped wind or a confirmed broad absorption line classification. That caution should remain explicit. What the paper does establish is that the quasar is the most luminous currently known, that its black hole is accreting near the Eddington limit, and that the relation between luminosity and mass accretion rate is affected by the structure and viewing angle of the accretion disk and disk winds. Those statements make a strong wind physically plausible without proving its exact observed form in this source. A quasar shining this intensely is expected to produce a significant radiative environment in which winds are natural, but the geometry, speed distribution, and observational signatures of the outflow for this specific object remain to be measured in greater detail. The region is therefore best understood as a layer of transfer. Matter that comes close enough to the nucleus is exposed to such strong energy release that some of it reverses course and departs. The gas becomes accelerated, ionized, and often spectrally visible in absorption against the bright inner continuum. Some parcels may remain relatively close to the nucleus. Some may merge into broader outflows that affect the host galaxy on much larger scales. The wind layer is not separate from the quasar's power source, but it is distinct in function. It takes a share of the liberated energy and turns it into motion, pushing mass outward through the surrounding regions. In this 12th section, the most luminous known object appears not as a still center of light, but as an active source of force, driving a fast ionized wind into the matter around it and marking the point where brightness becomes mechanical influence. Inside the wind layer, the quasar's radiance is rooted in a broad rotating flow of matter known as the accretion disk. NASA describes the accretion disk as the main light source associated with the black hole, a hot, bright, rapidly spinning disk formed as gas settles into orbit before continuing inward. In the case of J0529-4351, the discovery team identifies the extreme luminosity with a hot accretion disk and models the observed spectrum as disk emission seen at a modest inclination. This region is therefore not an accessory around the black hole. It is the principal machine by which in falling matter becomes visible light, ultraviolet radiation, and much of the power that later shapes the surrounding layers. The outer accretion disk is not a static ring. It is a flattened, rotating flow in which gas continues to lose angular momentum and drift inward over time. A major review of black hole accretion theory explains that internal dissipative processes remove angular momentum gradually, allowing matter to spiral downward while converting gravitational energy into heat and then into radiation that escapes from the disk surface. The important point for this region is that the disk shines because it is working. Gravity alone does not produce the observed brilliance unless orbiting gas can rub, stress, and exchange momentum within the flow. The outer disk is therefore a zone of orderly rotation made luminous by slow internal friction and energy release. On these scales, the disk remains comparatively cool relative to the most intense parts of the flow, though cool is only a relative term. NASA notes that gas closer to a black hole is hotter and emits more energetic radiation, which means the temperature rises steadily inward across the disk. In the outer region, the gas is still hot enough to radiate strongly, but its output lies more toward the optical and ultraviolet part of the quasar continuum rather than the harshest central emission. The disk, therefore, has a thermal gradient, with each radius contributing a somewhat different color and intensity. The outer layers do not merely support the inner ones mechanically. They add their own broad luminous surface to the total glow of the quasar. The material in this region is dense enough and opaque enough that the standard description treats much of the disk as optically thick. In simple terms, light does not pass straight through the flow as if through a thin mist. Instead, radiation is absorbed and re-emitted many times before escaping from the surface. This helps the disk behave like a thermal radiator, with its brightness linked to local temperature. Reviews of accretion disk theory describe this kind of disk as geometrically thin compared with its radius, but optically thick in the vertical direction. That combination suits a quasar well. The disk can extend over large distances while remaining relatively flat, and it can radiate efficiently because heat generated inside the flow gradually leaks outward through the disk surface. The scale of the disk in J0529-4351 is part of what makes the source so striking. ESO's Discovery release states that the light comes from a hot accretion disk about 7 light-years in diameter, a size the team describes as extraordinarily large. The Discovery paper likewise models the continuum with a standard accretion disk spectrum and uses that fit to infer the enormous luminosity of the system. Even allowing for uncertainty in viewing angle and radiative efficiency, the disk must be vast in order to sustain such power over such a wide radiating surface. In this outer disk region, that scale matters. The quasar is not powered by a tiny glowing point alone. It is powered by an extended rotating field of gas whose luminous area is immense by the standards of black hole systems. Its motion is disciplined by orbital mechanics. Gas at larger radii circles more slowly than gas deeper in the potential well, and the orbital time there is longer. This gives the outer disk a calmer character than the more compact inner flow. The gas still moves at tremendous speed in absolute terms, but the shear, heating, and emitted photon energy are all less extreme than at smaller radii. The region can therefore be understood as the broad working body of the disk, where matter remains fully engaged in accretion, but has not yet reached the most compressed and hottest part of the rotating flow. The luminosity seen from Earth includes light from this outer area precisely because the disk is large enough for many radii to contribute at once. The outer disk is also where the quasar's brightness begins to look smooth. Individual clouds or streams do not dominate the appearance. Instead, countless neighboring orbits blend into a continuous surface of radiation. This is one reason accretion disk models are so useful for quasars. They treat the flow as a series of annuli, or narrow rings, each radiating according to its local temperature, and together these rings build the broad continuum spectrum. The discovery analysis of J0529-4351 explicitly fits grids of disk spectra across black hole mass, spin, and inclination, showing that the observed brightness can be understood as the integrated light from a large thermal disk. Later work on the source has refined the kinematics of the nearby broadline gas and emphasized prominent outflow there. But the basic interpretation of the continuum as accretion-powered remains intact. Because the disk is extended, its appearance depends on angle. A disk seen more face-on appears brighter than the same disk seen farther from face-on, since the projected emitting area changes and relativistic effects alter the observed spectrum. The discovery paper for J0529-4351 therefore explores a range of viewing angles when fitting the continuum. This does not make the luminosity arbitrary. It means that careful modelling is required to separate intrinsic power from orientation effects. For the outer disk, the implication is straightforward. It is not only a luminous surface but also a directional one, a flattened radiator whose apparent brightness depends in part on how that surface is presented across the cosmos. This region has a quiet grandeur. Matter that once drifted through a galaxy, and its inner nucleus is now organized into a luminous disk many light-years across, rotating with persistence, shedding angular momentum, and radiating away the gravitational energy of descent. It is the broad thermal body of the quasar, the place where infall becomes sustained brilliance over a vast surface. In this 13th region, the most powerful known quasar is expressed not as a narrow beam or a single point, but as a great rotating disk of hot gas, extended, efficient, and bright enough to outshine entire galaxies while still obeying the calm orbital logic of accretion. Near the center of the accretion flow, the disk changes character. The broad outer body of the disk still matters, but closer in the gas becomes hotter, faster, and more compressed, and the released energy grows more concentrated. This is the inner disk and corona region, the hottest visible layer of the quasar before matter reaches the final boundary around the black hole. NASA describes the accretion disk as the main light source around a black hole, and notes that matter gradually works inward from the outer disk to its inner edge. In that inward progression, the inner disk becomes the most intense thermal part of the flow. The orbital speeds rise, the temperature rises, and the surface brightness rises, so that a great share of the quasar's energetic radiation is rooted in a relatively compact inner zone. The gas here is still arranged in a flattened rotating flow, but the motion is more extreme than in the outer disk. Each orbit lies deeper in the gravitational well, so the same amount of inward drift releases more energy than it does farther out. The disk remains luminous because angular momentum continues to be transported outward through stresses inside the flow, allowing matter to spiral inward while gravitational energy is turned into heat. In the inner disk, this process reaches its highest thermal intensity. The radiation emerging from these radii shifts toward the ultraviolet and extreme ultraviolet, and some of the energy is available to seed even higher energy emission in the region above the disk. For a quasar accreting near the Eddington limit, as the discovery paper reports for J0529-4351, the inner disk is therefore one of the most efficient radiating surfaces in the observable universe. Its appearance is also altered by relativity. NASA's black hole anatomy overview explains that near a black hole the disk spins so fast that relativistic effects become obvious, with the side rotating toward the observer appearing brighter and bluer, and the receding side dimmer and redder. Light from the far side is bent by the curved space-time around the black hole, so that the disk does not present itself as a simple flat ring. The inner disk is therefore not only hot, it is visually warped by gravity and motion. Even when telescopes cannot resolve a distant quasar disk directly, the same physics shapes the emitted spectrum and any reflected X-ray signatures from the innermost radii. The result is a region where ordinary orbital geometry is no longer enough to describe what the radiation does. Above this inner disk lies the corona. NASA's recent active galactic nucleus anatomy material names the corona as one of the principal structures around an active nucleus, and Hubble-based NASA reporting describes it as a very hot region hovering above the black hole that absorbs and reprocesses ultraviolet light from the accretion disk, energizing it into X-rays. In simple terms, the disk supplies a dense field of lower energy photons, and the corona boosts some of those photons to much higher energies. It does this through hot electrons, a plasma of charged particles that scatter the disk radiation and raise it into the X-ray band. This makes the corona the source of much of the quasar's high-energy output, while the disk remains the source of the underlying thermal radiation. The corona is not large compared with the rest of the quasar. Reviews of radio-quiet active galactic nuclei state that reverberation studies, in which reflected emission echoes coronal changes after a short delay, indicate that the corona is compact and typically smaller than about 10 gravitational radii. Gravitational microlensing studies likewise infer a very small X-ray emitting region in quasars, consistent with a compact corona close to the black hole. Even so, compact does not necessarily mean point-like. The same review notes that recent X-ray polarization results point toward a more extended geometry distributed along the inner disk plane rather than a perfectly spherical source or a simple lamppost point above the center. Observations therefore indicate a compact corona. It remains uncertain whether its true shape is best described as patchy, slab-like, vertically elongated, or changing among these forms with accretion state. Its plasma is extremely energetic. A recent review of coronal emission states that the primary X-ray emission in active galactic nuclei is believed to originate from a hot corona, with characteristic temperatures of about 10 to 100 kilo-electron-volts and with low to moderate optical depth. That language is technical, but the physical meaning is clear. The electrons are so energetic that when ultraviolet or soft X-ray photons from the disk pass through the corona, repeated scattering can lift them to much higher energies. The coronal spectrum therefore often appears as a power law with a high-energy cutoff, and that cutoff carries information about the electron temperature. The corona is not merely a glowing shell. It is a high-energy processing layer that changes the character of the disk radiation before it escapes into the wider quasar environment. The inner disk and corona are tightly linked. The Frontiers review on active galactic nucleus corona describes the accretion disk and corona as energetically and geometrically related, with strong empirical connections between ultraviolet disk emission and X-ray coronal emission. It also notes that optical and ultraviolet emission can echo variations in the X-rays after a delay corresponding to light travel time across the disk. This means the inner disk and corona do not behave like two unrelated objects placed one atop the other. They are a coupled system. Energy released in the accretion flow heats the corona, while coronal X-rays illuminate the disk, which in turn reflects and reprocesses part of that radiation. The boundary between the two is therefore active and reciprocal. The disk feeds the corona with seed photons, and the corona writes back onto the disk in X-rays. That reflected X-ray light is one of the main reasons the inner disk can be studied at all. A recent review of relativistic reflection in active galactic nuclei explains that X-ray observations reveal reflected emission from the innermost regions of accretion disks, and that these spectra contain general relativistic signatures produced near spinning supermassive black holes. The reflection becomes blurred and distorted because of high orbital speed, gravitational redshift, and light bending. In practical terms, the inner disk acts both as a radiator and as a mirror, though not a mirror in the ordinary sense. It reflects coronal X-rays after altering them, imprinting the conditions of the innermost flow on the observed spectrum. This is one of the strongest observational routes into the physics of the near-horizon disk, even when the region is far too small to image directly in a distant quasar. For J0529-4351, the direct observations so far emphasize the extreme luminosity of the disk and the near-Eddington nature of the accretion, while the detailed X-ray corona of this particular source has not yet been mapped with the same specificity achieved for some nearer active nuclei. The discovery paper models the continuum with an accretion disk spectrum and treats the source as one viewed at modest inclination, but the size, shape, and variability state of its corona remain uncertain. Even so, the broad scientific picture is secure. The most luminous known quasar must possess a fiercely radiating inner disk and a high-energy coronal layer capable of converting part of that radiance into X-rays. In this 14th region, the quasar reaches its hottest visible form, a compact inner disk of extreme orbital heat, capped by a corona of energetic plasma, together making the final luminous engine just outside the black hole's last boundary. At the deepest visible layer of the quasar lies the final boundary of the black hole, the event horizon. This boundary is not a surface in the ordinary sense. It is the limit beyond which light cannot escape back outward. NASA describes it as the region from within which nothing, not even light, can escape. And a major review of black hole accretion theory describes it as a one-way membrane rather than a rigid surface. That distinction is essential here. The most luminous object yet observed is powered by a black hole. But the black hole itself is not the bright thing. The brightness belongs to matter outside the horizon, still visible, still radiating, and still able to send energy into the universe before it crosses the final line. This is why the inner engine of a quasar can appear paradoxical. The central object is dark by definition, yet the region around it can outshine whole galaxies. The reason is simple in physical terms. Matter falling inward loses gravitational energy before it disappears from view. As gas spirals through the inner disk, friction-like stresses and compression heat it intensely, and that heat is radiated away as light. By the time the gas crosses the event horizon, most of the visible power has already been generated outside it. NASA states plainly that accretion disks of hot material around black holes emit X-rays and other forms of energy, while the black hole itself traps anything that passes through the horizon. The light comes from the descent, not from any shining surface inside the hole. Just outside this final boundary lies the last stable part of orbital order. NASA's black hole accretion disk visualizations identify an innermost orbit matter can occupy before plunging into the black hole. This is the innermost stable circular orbit, often shortened in technical writing to ISCO. Outside it, gas can still follow relatively stable paths while radiating strongly. Inside it, stable circular motion is no longer available, and the gas enters a plunging flow. The change is important because it marks the transition from luminous orbiting matter to rapidly disappearing matter. The disk does not usually extend inward in the same orderly fashion all the way to the horizon. Instead, there is a last stable orbit, then a plunge region, then the event horizon itself. The black hole's spin helps determine how close this last stable orbit can lie to the horizon. NASA notes that a rotating black hole can host stable material much closer to its event horizon, than a non-rotating black hole can. This means spin changes the geometry of the deepest visible region. If stable gas can circle closer in, then more gravitational energy can be released before the gas disappears, and the accretion flow becomes more efficient at turning infel into radiation. In calm language, a faster spinning black hole allows the engine to work deeper in the gravitational well. That does not mean the horizon itself shines. It means the orbiting gas outside the horizon can reach more extreme conditions before the plunge begins. Once matter passes the horizon, the visible story ends. No photon emitted from within that boundary can return to a distant observer. This is the sharpest physical break in the whole structure of the quasar. Every outer region can still send some kind of signal. The narrow-line gas shell glows, the torus re-radiates, the broad-line clouds emit, the winds absorb and scatter, the disk radiates thermally, the corona produces X-rays. The horizon alone does not return anything once crossed. For that reason, the central darkness is not an empty decorative hole surrounded by light. It is the actual point at which observation stops. The engine is visible right up to the threshold, and then it is gone. Even the famous dark center seen in black hole imagery is not the event horizon itself in a simple direct sense. NASA and Einstein Online both explain that the dark region seen in black hole images is the shadow, enlarged by gravitational lensing and by the capture of light near the hole. Einstein Online notes that the image shows glowing gas orbiting the black hole at high speed, while the dark region is not the horizon itself but the shadow produced as light is bent by gravity. NASA adds that thin rings of light appear around the shadow because light from the accretion flow can orbit the hole multiple times before escaping. Near the final boundary, then, even appearance becomes a product of curved space-time. Light does not travel in straight, simple paths. It bends, loops, fades, and sometimes escapes only after circling the abyss. For J0529-4351, this inner engine reaches an extreme now known nowhere else. ESO reports that the central black hole has a mass of 17 billion suns, grows by the equivalent of about 1 sun per day, and is surrounded by a hot accretion disk about 7 light-years across. ESO also reports that the source shines more than 500 trillion times more luminously than the Sun, making it the most luminous object yet observed. These numbers belong to the radiating matter outside the event horizon, not to the darkness beyond it. They describe how much energy the disk and its innermost regions release as gas approaches the final boundary around an enormous black hole. The horizon is the silent center of this brightness, not its visible emitter. This last region therefore contains the clearest statement of what a quasar is. It is not a bright hole in space. It is a dark gravitational boundary, wrapped in the most efficient luminous descent nature seems able to sustain on vast scales. Stable orbits end. The plunge begins. The horizon takes in whatever crosses. Around that one-way edge, gravity bends light. Spin sets the depth of the visible engine, and matter radiates away extraordinary power in the final moments before disappearance. In the deepest inner region of the most luminous known object, the universe reveals a quiet arrangement of opposites, perfect darkness at the center, and record-breaking radiance born just outside it. Far from the Earth that later receives its light, the quasar continues to shine in the same quiet arrangement. A young universe surrounds it. Expanding space carries its signal outward for billions of years. The cosmic web supports the dark halo. The halo holds the galaxy. The galaxy keeps its wide gas reservoir and its inward-moving streams. The crowded nuclear region surrounds the active center. Ionized clouds glow farther out. dust reshapes the light into warmth. Vast clouds circle close in. Winds rise and carry force back into the host. The great accretion disk turns descent into radiance across a surface wider than many would expect around a black hole. Deeper still, the inner disk and corona gather the harshest energy. At the center, the event horizon remains dark and silent while everything just outside it shines with extraordinary intensity. In this way, the most luminous known object in the observable universe is also one of the clearest expressions of a simple rule. Gravity gathers matter, matter falls inward, and falling matter gives up energy before it disappears. Nothing in this deep structure is hurried. Even its violence appears calm at a distance, translated into light that crosses the universe with patience. By the time that light reaches human instruments, the quasar's age, its setting, and its power have all been written into the signal. The galaxy around it may remain hard to isolate. Some details of the inner wind or surrounding gas may still wait for future measurements, yet the central picture is already clear. A black hole does not shine by itself. The brightness belongs to matter nearing the edge of no return, orbiting, heating, and radiating in the last visible moments before the final crossing. Around that darkness, the universe arranges one of its greatest displays of energy, not as a sudden outburst alone, but as a long sustained blaze held together by gravity, motion, heat, and time.